Welcome to today's Explainer. We are going to be unpacking a really major breakthrough in how artificial intelligence is actually learning to listen to, evaluate, and truly understand audio. If you've ever wondered how developers are trying to push the absolute boundaries of audio quality in telecom or even synthetic speech, well, you are in exactly the right place. Let's get right into it. Picture this. You're on a VoIP call, maybe a Zoom or Teams meeting, right? The audio is perfectly fine, crystal clear for 10 straight minutes. Then suddenly, out of nowhere, you get this weird 2-second robotic glitch that totally scrambles the sound. And then it's just gone. It happens all the time, but it raises a really fascinating question. How on earth can a computer system pinpoint that incredibly brief, fleeting flaw hidden inside a massive sea of otherwise perfect audio? To unpack this, here is our roadmap for the explainer. We'll start with number 1, the local audio glitch. 2, we'll meet the paper. 3, look at their 2 key innovations. 4, peek inside the architecture. 5, break down the results and impact. And 6, finish up with future applications. All right, kicking things off with section 1, the local audio glitch. Let's look at why spotting these micro flaws is currently so incredibly hard for an AI. So here's the core issue. Traditional systems use something called Global Subjective Speech Quality Assessment, or Global SSQA. They listen to a whole audio file and just slap a single generic score on it, like, hey, this is a 4 out of 5. Now, a 4 sounds pretty great, right? But the problem is that broad brush completely misses those tiny, isolated glitches that absolutely ruin the modern listening experience. What we really need instead is local SSQA. That's a system evaluating audio frame by frame, continuously, to pinpoint exactly where things go off the rails. So how do we actually build that? That brings us to section 2, Meet the Paper, where a new academic study proposes a highly structured way to solve this. The research we are dissecting today is titled Speech Quality Embeddings for Improved Detection and Classification of Degradations in Speech Signals. This comes from an incredible team, Michael Coleman, Tobias Kurd-Landwehr, and Reinhold Hombaumbach, over at Paderborn University in Germany. They basically set out on this mission to train an AI model to listen, localize, and classify audio degradations with the exact precision of a professional human audio engineer. And the authors really hit the nail on the head right away. They state that the expressivity of a global score is limited and simply cannot inform the user about temporally constrained artifacts in the speech. Basically, a single overall score just doesn't cut it anymore. Today's synthesis and transmission systems are so high quality that the flaws are hiding in the micro details, and traditional global scoring is completely blind to them. To fix that massive blind spot, the researchers got creative. Here is section 3. 2 key innovations, where they fundamentally changed how the AI is trained. Their first innovation is what they call a partial mix-up strategy. You can think of this a lot like training a search dog using a synthetic decoy. See, there just isn't enough existing data out there that manually labels every single microglitch frame by frame. So the researchers just made their own. They take a perfectly clean audio file, intentionally mix in chunks of heavily degraded audio, and boom, they generate strong frame-by-frame pseudo-targets. They've essentially handed the AI a perfect treasure map, showing exactly where the bad audio lives. Now, their second innovation is a training technique called supervised contrastive loss. Honestly, this blew my mind. Think of it as forcing the AI to perfectly sort different types of audio glitches into highly specific, distinct buckets in its digital brain. If that first innovation tells the AI where the glitch is, this one teaches it what it is. It mathematically forces robotic distortion to group tightly over here, static noise to group tightly over there, and ensures all of those flaws are kept miles away from the clean audio profile. All right, let's move on to section 4, inside the architecture, and actually peek under the hood to see how this works in the neural network. It starts with the raw speech signal entering the encoder. The team specifically used a really powerful pre-trained model called Wave2Vex-2-large. This encoder acts as the ears of the operation. It listens to the continuous audio and mathematically chops it down into dense frames at a rate of 50 times per second. Just think about that volume of data for a second. It's slicing every single second of a call into 50 distinct pieces and evaluating each one. It's a massive undertaking, but it gives the AI incredible resolution. Then we get to the next step, which is an absolute stroke of genius. The architecture actually splits into a dual-head decoder. The top path, called DEC-MOS, predicts your traditional frame-by-frame quality score. But that bottom path, DEC-SCL, that is entirely dedicated to forming those highly specific cluster degradation embeddings we just talked about. It's analyzing the fundamental character of the audio in real time, not just lazily grading it on a 1 to 5 scale. So the real magic is how these embeddings are used for detection. Instead of just relying on a traditional quality score and saying, oh, the score dropped below a 3, must be a glitch, this system uses embedding-based detection. It takes the incoming audio frame and compares its spatial similarity against a pristine, clean reference. If the new audio deviates from that clean profile in a specific mathematical direction and matches one of our glitch buckets, the AI knows exactly where the audio degraded and exactly what kind of degradation it is. But hey, Siri is one thing. Let's get to Section 5, the results and impact, because the performance jump they recorded is absolutely huge. 0.91. That is the intersection AUC metric achieved by their contrastive embedding model on in-domain data. To put into perspective just how revolutionary that number is, the baseline model, using the old scoring method, scored a 0.01. That's not just an incremental improvement. That is a staggering, game-changing leap in an AI's ability to accurately detect the precise boundaries of a localized audio glitch. And when you actually map this out over time, the visual difference is undeniable. With the embedding-based detection on the bottom, you can see the AI's detection signal maintains a massive, totally clear margin to the threshold. It instantly spikes the millisecond to glitch region begins, and it drops the exact millisecond it ends. Now compare that to the old MOS-based method on the top. It's super noisy, barely crosses the threshold, and is just vague. The embedding method is just leagues ahead in sensitivity and precision. Which brings us nicely to our final section, number 6, future applications. What is the real-world impact of all this highly specific audio research? The applications here are incredibly exciting for the future of audio tech. Right off the bat, developers can finally pinpoint exact artifact locations in hours-long audio files without forcing a human to listen to every single second of the tape. But even cooler, because the AI classifies the specific type of glitch, engineers can query massive databases to pull up, say, every single instance of robotic distortion. They can then use that highly targeted data to train and drastically improve next-generation text-to-speech models. And that leaves us with a truly fascinating thought to wrap up on today. As this technology perfects itself, allowing developers to relentlessly hunt down and eliminate the absolute smallest, microsecond flaws in generated audio, how long until synthetic speech becomes completely, undeniably indistinguishable from reality? It's coming faster than we think. Thanks so much for joining me on this explainer, and we'll catch you next time.